Like all transport category airplanes, ATR 42 and 72 are certified to fly in atmospheric icing conditions. The airplane is equipped with systems that can detect, prevent and remove ice from critical areas of the airplane. Hi, my name is Magnar Nordahl. I'm an ATR typewriting instructor and airline captain. Today, I will talk about ice and rain protection systems on ATR. Before you watch this video, you may find it useful to see the videos I made for electrical systems and avionics. You will find links in the description below. This video will show the main features of the ice protection systems in all ATR variants. If you want to study the systems carefully, you must use the FCOM, the Flight Crew Operation Manual, for the variant you are flying. This may take a little more time, a few hours. If you are rated on ATR, you will know this system by heart. But there might be a few things you may not be aware of, so stay tuned. ATR defines atmospheric icing conditions as the following. On ground, when SAT, static air temperature, is plus 5 degrees Celsius or less, and in flight when TAT, total air temperature, is plus 7 degrees Celsius or less, and visible precipitation and or visibility must be less than 1500 meters. When I talk about temperatures, I will always use degrees Celsius. Atmospheric temperature is called SAT, static air temperature. TAT, total air temperature, is SIT plus adiabatic heating caused by the increase of local air pressure, for example at the wing leading edge. Unknown to many non-aviators, water drops can maintain the liquid state even when they are cooled to a temperature well below freezing. In theory, small cloud drops can reach temperatures as low as minus 40 degrees before they freeze. However, most ice forms when the temperature is close to zero. Small drops freeze quickly when they hit an object. They form rime ice, which is white. Large drops need more time to freeze and tend to drag along the surface as it freezes. This results in clear ice, and it can build up rapidly. A mix of large and small drops may result in horn ice, which can result in a huge increase in drag. An accident in 1994 gave ATR 72 a bad reputation when it comes to icing. This accident happened because the airplane entered freezing rain, causing severe icing on the airframe, a condition no airplane is certified to operate in, and because the flight crew did not understand the seriousness of the situation. In the aftermath of this accident, ATR has improved the ice protection systems, procedures and training. As long as you follow the guidelines set by the manufacturer, the airplane is safe as any other airplane. In my next video, I will discuss this in more detail. The ice protection systems protect critical surfaces that faces the airstream in flight. The systems are detection, probes heating, windshield heating, propeller heating, horns heating, side window heating, pneumatic boots for engines, wings and horizontal stabilizer, windshield wipers, APM, automatic performance monitoring, and engine compressor inlet. The following areas are not protected: nose cone, antennas, vertical stabilizer, wing fairing, landing gear fairings, flapjacks fairings, and propeller spinners. The ice protection systems are controlled from 3 panels on the overhead panel. The first panel consists of probes heating and windshield heating. They also call level 1, and they are always on during flight. The second panel consists of controls for propeller heating, horns heating, and side window heating. They are called level 2, and they are on when you're flying in atmospheric icing conditions, as I defined before. The third panel controls pneumatic de-icing boots installed in engine air intakes leading edges of the wings and the horizontal stabilizer. They also call level 3, and they are on when ice accumulates on the airframe and until you leave icing conditions. There are 10 different ATR variants in production, or had been in production. To make it a little easier, I have collected them into 3 groups. The first group consists of ATR 42-300 and 320. The only difference between them is the power of the engines. I call this group ATR 42-300. The second group consists of ATR 72-100, 200 and 210. The 100 is identical with the 200, but has a reduced max takeoff weight. The 210 is also identical to the 200, with the exception that the engines are more powerful. I call this group ATR 70-200 because this was the most produced variant. The third groups consist of 42-400, 42-500, 42-600, 72-500 and 72-600. They all have 6-blade propellers. The 42-400 is a 42-500 with less powerful engines, and just a handful were built. The 500 and the 600 variants are identical. I call this group ATR 500 onwards. Your first line of defense is the temperature indicator and the weather radar. The echo from the weather radar vary in intensity as a function of the droplet size, composition and quantity. What you should have in mind is that even a green radar return may result in severe icing. I have experienced just that. Visual indications might be subtle because you may not see ice form on the wings, especially when it's dark. And it might be difficult to detect clear ice even in daylight. You may see ice form on the windshield wipers, and in the ATR 42 you can see the spinner as well. And here are some warning signs you cannot neglect. 1. Water streaming on the windshield and the side windows. 2. Ice forming on the side windows. 3. Loss of performance, such as rate of climb or cruise speed. To assist detecting ice on the aircraft, an ice evidence probe is installed below the captain's side window. It is shaped like a small wing profile. It has an internal light, which is illuminated when the navigation light is on. As long as there is ice on the ice evidence probe, we must consider that the other areas of the airplane are contaminated by ice. When watching the ice evidence probe from above, you may not notice that this might be horn ice. To be sure, you have to lean forward and have a look. Under the left wing there is an electronic ice detector. It's a small probe that vibrates with a constant frequency. When ice forms on the probe, as little as half a millimeter is enough. The weight of the ice causes the probe to vibrate at a different frequency. This triggers an icing alert in the cockpit. In aircraft with AFIS cockpit, the alert is an amber icing light on the ice detect panel. In aircraft with glass cockpit, the alert is an amber icing message in the FMA, the flight mode annunciator. The ice detector probe is then heated for 7 seconds. If ice accumulation is detected within 60 seconds, the icing alert remains on. If ice accumulation is not detected after 60 seconds, the icing alert extinguishes. However, the ice detector is not perfect. Under certain conditions, ice may sublimate from the detector at the same rate as it builds up, and the alert will not be triggered, even when ice may build up on other areas of the aircraft, such as the wings. And more critical, large supercooled water drops may not freeze on the detector when the static air temperature is slightly below 0, but they may form clear ice on the wings. Therefore, we pilots must be vigilant when we are flying in icing conditions. Our number one priority is always to maintain a safe speed. As I said, the ice detector is very sensitive. On the 72-600, I have experienced that the ice detector can trigger icing alert when raindrops stick to the probe during taxiing. even when the temperature is plus 30. I never experienced this with early ATR variants, so what is your experience? Let us know in the comments below. Pitot tubes, static ports, angle of attack probes, and temperature probes are heated. Most of the probes are heated by 115 volt AC wild power. AC wild is AC variable frequency. However, the static ports are heated by 28 volt DC power, and the standby pitot tube is heated by AC constant frequency power via inverter number 1, which is powered by DC power. Normal procedure is to switch the probe heating on after engine start and off after landing. This will prevent injury if somebody should touch the standby pitot tube while the aircraft is parked on the ground. Been there, done that. Starting with the first ATR variant, the 42300, the control panel for the probe heating looks like this. The captain push button controls pitot heat, static port heat, and angle of attack probe heat for the captain's instrument. Alpha means angle of attack. Likewise, the first officer push button controls pitot heat, static port heat, and angle of attack probe for the first officer's instruments. The standby push button controls pitot heat and static port heat for the standby instruments, and heating of the TAT probe, total air temperature. Compared to other variants, the ATR 42300 has only one TAT sensor. So why are there no alerts for the static port heating? That's a good question, because it's important to know whether it's working or not. The static ports are flush with the fuselage, and ice will not form during flight, but snow and ice may cover the static ports while the aircraft is on the ground. Therefore, static port heating is only monitored when the aircraft is on the ground. On the 42300, the alert is coupled to the pitot alert. And the logic is as following. If you get an amber pitot alert before takeoff, it's either the pitot heat or the static port that has failed. You will return to the ramp and get the problem solved. If you get an amber pitot alert in flight, it's the pitot heat that has failed. You open a QRH, the Quick Reference Handbook, and follow the procedure there. If you get an amber pitot alert when touching down, you are pretty sure that this is the static port heating that has failed. Thankfully, when ATR designed the next model, the 72200, they modified the control panel to include a caption for static port heating. They also added one more TAT sensor and put them under the wings, clear of the sun. And later on, the color of the panel changed from brown to Airbus blue. However, static port heating remains monitored only when the aircraft is on the ground. TAT heating is inhibited on the ground, otherwise the temperature indication will be excessively high. Therefore, you will never see an amber TAT caption when the aircraft is on the ground. Note: if a probe heat fails in flight, don't switch off the push button. You can reset it once, but you must leave the push button on because this push button controls up to 3 of the heating elements. Always read your checklist carefully. Okay, are you still with me? The next system is much easier. The windshields have a thin film of gold embedded between 2 layers of glass. It is supplied by 200 volts AC wild electrical power. The temperature is electronically controlled. The auto temperature is plus 2 degrees or more, and the inlet temperature is plus 21 degrees or more. Normal procedure is to select the push buttons on before the first flight of the day and off after the last sector before we leave the airplane. The inner part of each propeller blade leading edge has a heating element. The outer part is not heated because the adiabatic heating is sufficient to prevent ice to form. The heating elements are powered by AC wild, but only when the NP, the propeller speed, is above 63%. This prevents damage when the propeller is not turning. The electrical current is transferred via brushes on the propeller gearbox to metal rings on the propeller spinner bulkhead. Every second propeller blade are heated together. On 4-bladed propellers, blades number 1 and 3 are heated, then blades 2 and 4. On 6-bladed propellers, blades number 1, 3 and 5 are heated, and then blades 2, 4 and 6 are heated. When SIT, static air temperature, is between 0 and -10, the propeller blades are heated for 10 seconds at a time. When SIT is below -10 degrees, the propeller blades are heated for 20 seconds. ATR calls this high power cycle, but it's only the time that is increased. ATR variants with 4-bladed propellers have manual switching. When propeller anti-ice is active and SIT drops below 10 degrees, you activate the 20-second cycle by pressing this button. In ATR 42300 and 320, there's a timer for this purpose. In ATR 72200, the timing is controlled by the MFCs, the multifunction computers. ATR 500 onwards, they have 6-bladed propellers, and the switching between 10 and 20-second cycles is automatic because the MFC receives temperature information from the air data computers, ADC. A failure to the MFC or the air data computers will trigger an amber fault light in a mode select push button, and the high power cycle is automatically activated. The procedure is to revert to manual control of the timing as I described just a moment ago. All primary flight controls, ailerons, elevators and rudder have aerodynamic horns that make it more easy for the pilots to control the aircraft. They are heated by AC wire electrical power. There are 2 push buttons. The left push button controls rudder and left elevator horns heating, and the right push button controls ailerons and right elevator horns heating. When one of the push buttons is pressed in, a green icing AOA light illuminates on the ice push button. On the 600, there's also a green icing AOA label on the FMA. The green icing AOA lights indicates that the stall warning system is in icing mode, and the angle of attack threshold for stick shaker and stick pusher is reduced. To compensate for this, minimum safe speeds must be increased. When you fly with an AFIS cockpit, you find icing speeds in the Quick Reference Handbook, the QRH. When you fly with a glass cockpit, the FMS automatically increases the speeds. The icing AOA light does not extinguish when you select horns heating off. The reason is that it may still be ice on the airframe. The light can only be extinguished when the horns heating is off and you press the push button. But before you do that, you must be sure that the ice evidence probe is free of ice. The forward part of the side windows is heated by DC electrical power. The temperature is electronically controlled and the inner temperature is plus 21 degrees or more. The heating prevents fog on the window when the outside humidity is high. If both windshield heating elements have failed, the pilot may be able to see the runway through the heated portion of the side window. The engine air intakes and gas paths have pneumatic boots that break loose any ice that may form. The gas path is the duct from the air intake to the oil cooler radiator and up to the engine. Wing and horizontal stabilizer leading edges have boots that are oriented chordwise, and every second row of boots are labeled A and B. The boots are inflated by bleed air at a pressure of 20.3 psi and deflated by a venturi supplied by the same bleed air. Each section is inflated for 5 seconds. This video shows how the boots on the horizontal stabilizer works. The timing sequence varies between ATR variants as they have different number of boots on the wings. This figure shows the sequence for the 72500 and 600. Fast mode is used when SIT is above -20 degrees. The sequence starts every 60 seconds. Slow mode is used when it's colder, and the sequence starts every 180 seconds. The 42-300 has two wing boots outside the engines. Later ATR 42 variants also have inner boots between the fuselage and the engines. Early ATR 72-200s have three wing boots outside the engines, but no inner boots. The inner boots were introduced later on the 72-200 and become standard on later variants. The control panel for the 42-300 has a push button to switch between fast and slow modes, and the inflation sequence is controlled by a separate timer. The temperature where you select slow mode is -18. All other ATR variants use -20 degrees, which is easier to remember. The 72-200 introduced the MFC, the multifunction computer, which controls the inflation sequence. In case of MFC failure, you get an amber fault light in the mode select push button. A standby timer will then take over. However, selection between fast and slow modes is still manual. As I mentioned earlier, ATR 500 onwards have MFCs that receive air temperature information from the air data computers. Therefore, the switching between fast and slow modes is automatic. To sum it up, the guarded mode select push button is related to the MFC only, and it controls the timing of the cycles of the boots. The mode select push button is related to the MFC and the air data computers, and controls the automatic switching between the temperature-dependent modes for the propeller anti-ice and boots de-ice. The windscreen wipers are controlled with two knobs on the overhead panel, one for each pilot. The wipers have two speeds, slow and fast. When selected off, the wipers return to park position. You should consider slow to be for taxi and fast to be for flight. However, the wipers are not able to cope with severe rain. In such cases, you should consider to delay your takeoff or approach, or even go around. Not only because of the limitation of the wipers, but also because of the risk of aquaplaning. And please do not use the wipers on a dry windscreen. The windscreen might be scratched. The APM, Aircraft Performance Monitoring, is part of the multi-purpose computer, the MPC, which was introduced with the 500 variants in 2005. The MPC can be retrofitted into earlier aircraft. The APM monitors aircraft performance in flight. The APM compares aircraft theoretical drag with actual drag and alerts the flight crew if abnormal loss of aircraft performance occurs. The warnings are triggered if one or several of the following conditions are met and SIT is below 10 degrees Celsius. Icing AV light is illuminated. De-icing airframe push button is selected on. Ice accretion is detected. In an AFIS cockpit, the APM control panel is located to the right of the first officer's flight instruments. There is an on-off push button, a test button, and a weight selector. Before takeoff, the selector is set to the position nearest the actual takeoff weight. And during flight, the APM calculates the fuel flow, which means that the calculated weight decreases. Because the fuel consumption is subtracted from the weight you set before the previous takeoff, it is important that you, before the next takeoff, turn the knob at least one notch in order to set the new takeoff weight. On ATR 600 variants, the control panel has an on-off push button and a test button only. The weight information is provided by the FMS. The APM issues 3 levels of alerts. 1. Cruise speed low. Abnormal drag reduces the cruise speed with more than 10 knots. However, this condition may also be caused by a downdraft. So take a look at your ice evidence probe. 2. Degraded performance. This is an abnormal increase in drag, most likely due to ice accretion. It causes reduced cruise speed or rate of climb. This might indicate severe icing, and action must be taken to maintain a safe speed. My next video will be about some incidents where the flight crew neglected this alert and put the airplane in a dangerous situation. And 3. Increase speed. Indicated airspeed is less than icing bug plus 10 knots. The icing bug is minimum speed with the flaps retracted in icing conditions. Now we are really in a critical situation, and if you haven't applied the procedure for severe icing before, you better do it now. Your main priority is to increase the speed. Here is something you may not be aware of. The engine compressor inlet lip is hollow and filled with engine oil. The heat from the oil prevents ice to form on the inlet lip. Because of this, the oil temperature must be at least 45 degrees when you fly in icing conditions. There is at least one incident where an engine has flamed out because the oil got too cold. This was on British Airspace ATP, which has the same type of engines as ATR. The oil cooler flaps had been stuck in full open position, and when the power levers were set to flight idle during a high-speed descent, the oil temperature decreased, which caused ice to form on the inlet lip. When the aircraft descended into warmer air, the ice melted and was ingested into the engine, which flamed out. However, the crew restarted the engine without problem. ATR aircraft have a Memo panel. In variants with AFIS cockpit, it provides information about the status of the cabin signs, continuous ignition, de-icing, propeller brake, and fuel crossfeed. In variants with glass cockpit, some of the information is moved to the other displays, and the Memo panel provides information about fuel crossfeed, anti-icing systems, de-icing systems, and cabin signs. Before we start the engines, the ice protection panel looks like this. Probes heating are off, windshield heating is selected on but is not powered, and airframe air bleed is not pressurized. After starting the engines, the panel looks like this. Probes heating are selected on, windshield heating is active, and airframe air bleed is active. If SAT is +5 or less, and there is water, slush, or loose snow on the runway, we have ground icing conditions. We will activate propeller heat to protect the propellers from spray from the wheels. However, the wings are not affected, and we will use speeds for normal conditions. If there are atmospheric icing conditions at takeoff, or if we anticipate icing conditions shortly after takeoff, we engage all anti-icing systems and use icing speeds. The icing AV light is now illuminated. Likewise, before we enter icing conditions in flight, we engage the anti-icing systems. When ice accumulation is detected, either visually or by the ice detector, we engage the de-icing systems. When ice accumulation ends, but we are still in icing conditions, we do not change anything. When we exit icing conditions, we switch off de-icing and anti-icing systems. The airplane can be landed with anti-icing and de-icing systems operating. And when the ice evidence probe is free from ice, we can push the icing AOA push button and resume normal speeds. That's it. The ice protection systems are pretty much straightforward. They either work or they don't. Just remember the following oddity with the 42300 and the P2 alert. Before takeoff, it's either a failed P2 hit or a failed static port hit. In flight, it's a failed P2 hit, and at touchdown, it's most likely a failed static port hit. And remember, on all other ATR variants, the static alert can only be activated on the ground, and the TAT alert can only be activated in flight. There is only one failure that requires some deeper understanding, and that's when it happens to the airframe air bleed. Here is the de-icing system and it's selected on. Each engine supplies bleed air which passes a temperature sensor and flows through the de-ice valve. From here the bleed air takes two directions, either to the engine de-icing boots or through the isolation valve to the airframe de-icing boots. Downstream of the isolation valves, there is a pressure sensor. An amber airframe air bleed fault light indicates that there is an engine bleed overheat or that the bleed air pressure to the airframe de-icing boots is too low. The procedure is to select airframe air bleed off. The isolation valves are then closed and the pressure sensor is neglected. Then you wait. Depending on the checklist and the variant of ATR, you wait 6 or 10 seconds. If there is an overheat, an amber fault light will illuminate within this time on the associated engine's de-icing push button. Then the procedure is to switch that push button off and select the airframe air bleed back on. This action will close the de-ice valve on the affected side, preventing engine de-icing on the affected side, and open isolation valve on the other side, allowing the other de-icing systems to be supplied by bleed air from the other engine. If there is no engine de-ice fault light, then there is no overheat, and the fault alert is caused by loss of pressure. The airframe de-ice push button is then selected off, and the airframe air bleed push button is left in the off position. Always read your checklist carefully. Okay, that's all for this time. If you have questions about this or other systems, please use the comment section below. I will be happy to reply. And thank you for all of you who give me positive feedback and ask questions. I really appreciate it. And please support the channel by sharing with your friends, press the subscribe button and the notification bell. Have a wonderful day and happy landing!